Okay, good afternoon and welcome to Statistical Mechanics. So let me recap where we were last time. Unfortunately, I didn't record last time's lecture, so I just want to recap the main point as I usually do when we're in class. So what we talked about last time was the density matrix, and I'm not going to go through everything that we did last time. But what we introduced it as an alternative formulation of quantum mechanics, and when we talk about as an alternative formulation of quantum mechanics, that's what we will call a pure state. And then we also talked about it as a mechanism for writing down quantum statistical mechanics, and that we called a mixed state. And the idea of a mixed state was that the system is in an incoherent superposition of states, and so in that way we capture the way that we're looking at an ensemble of different quantum mechanical systems that are completely isolated, and we're just simply averaging the results that we get from them. Now, the other thing that we did was we showed that if I have a system with only one state, I define the density matrix as shown over here on the left. Then that implies that it has the property of being idempotent. And that just simply means that the operator is its square. And then we also worked out what the equation of motion for the density matrix is, and that's shown here. And of course, this equation mirrors what we saw in classical mechanics, which is Liouville's theorem. So the important point about mixed states is that we now write the system down as an incoherent superposition of states, and the probabilities of those states, and these n's are eigenstates, those probabilities can be anything you like in principle, but in statistical mechanics, we take those probabilities to be given by the Boltzmann distribution, like so. And once that is the case, then what we end up with is a description which looks like this. We find that the density operator looks like eta minus beta times the Hamiltonian over z like this, and we interpret this as a sum of k equals 0 to infinity of minus beta times the Hamiltonian operator to the power k over k factorial. And with this definition, then the expectation value of any quantum operator then is simply the trace of the density operator times the operator that we are thinking of. And so this is just what the normal thermal average that we're used to, but now written down in terms of this operator. And then at the end of last lecture, what we did was we wrote down the corresponding formulae for the grand canonical distribution, which is pretty much as you would have expected, and so nothing special there. All right, Mark has his hand raised. Do you have a question, please?
Can you hear me?
A little bit, yes.
What about now? Is that better?
You're a little bit faint, but go ahead with your question. I'll see if I can answer it.
Is the mixed state density matrix idempotent too?
I'm sorry, I couldn't hear it. Can you please say it again? No, no. So being idempotent is a necessary and sufficient condition for being a pure state. Okay, so all right. So let me go on then. So what I want to do now in today's lecture is I want to give an example of this rather abstract formalism in action. So today my plan is this. First of all, I'm going to give an example of pure states. Then I'm going to give an example of mixed states. And then if we get time, we'll go on to we'll start the next major topic, which is interacting systems. And the systems that I'm going to use for today's examples are going to be spin systems. And so what we're going to do is we're going to look at the how to just do a simple calculation for a system in a pure state, and compute the how you take expectation values of spins in quantum mechanics, and then we're going to do the same thing for mixed states, and we're going to use that to work out the formulae for the quantum paramagnet. So I think my experience is that in teaching this before is that the examples make everything much clearer than what we saw in the previous lecture, which was completely formal. All right, so this is part 7, and this is a density matrix for a single spin. And this is going to be in a pure state. So what we're going to assume is that our system is a spin with a spin 1/2, and I'm going to use as basis functions just the usual phi1 is 1, 0, and phi2 is 0, 1, and that just means a spin up and down the z-axis. Okay, so just like you've done before. So now what I want to do is I want to write down a pure state. And I'm going to write down the pure state psi as some linear superposition of this basis. So we can write it down as phi1 and phi2. And so the matrix, the psi, or vector psi in this basis is just the row vector, the column vector AB. And because of normalization, we have that A squared plus B squared, the absolute value of, is equal to 1. So now then, if we write down what is the density matrix, so the density matrix in this basis is A star, B star A, B A star, and B star. And that's just using the formulae that I wrote last time. Okay, so let's give you an example of how to compute expectation values. So what our goal is to compute expectation values using this formalism. So let's suppose, for example, that the spins, or the spin in the system, is in the up state. So what that means is that the absolute value of A is equal to 1, that B is equal to 0, and so then that the density matrix is just going to be 1, 0, 0, 0. Or at least that's something that it can be taken to be. So now let's suppose that we take another state. So this state I'm going to take is this one. So psi is 1 over the square root of 2 for normalization, and then a mixture of this state, the up state, and the down state, that like this. And this state, what does it represent? So the answer is a spin along the y direction, and we can compute the spin components as I'm going to show you. So now then, what is the density matrix? So in this particular case, it's now this operator 1 1 1 1, like so, and if I were to write down, so that's just how to write. So that just, we'll see why this is so. But this is just how you write down the density operator. So another question you might ask: so given rho, what is the state? So let's, for example, consider this state: 1/2, 1, -1, -1, and 1, and this one is given by the following. The answer is this. So it's 1 0 minus 0 1, and you can check that that would work. I've got to normalize it by 1 over the square root of 2. So that looks like it would be the answer, but actually it's not the answer, because I could multiply this by any phase factor, phi, like this, and any value of phi would still satisfy this equation. So any pure state determines rho uniquely, but rho only determines the pure state up to an overall phase factor. Okay, so now let's that's fine. So now we know how to go back and forth between a density matrix and the pure states. So now let's calculate the. Now let's look at the interpretation. So what we wrote earlier was that the diagonal elements give the probability of finding a particular state. So let's suppose we take the first example. So we say that rho is the matrix 1 0 0 0. So in this particular state, then here, this one says that the probability of being in the up state is 1. The probability of being in the down state is equal to 0, and that is indeed what we started off with. So that's example number 1. Let's try another example. So in this example, let's say rho is 1/2 1 1 1 1. This is the first example we took before. So then this says that the probability of being up and the probability of being down is equal to 1/2. And if I look at this example, rho is 1/2, 1 minus 1 minus 1, 1, we find the same thing. Now, the off-diagonal elements I haven't said anything about. So these give us something to do with the quantum coherence. So we can sort of see kind of how that works by computing an observable. So what I'm going to do now is I'm simply going to compute the spin component in the y direction. And if I want to compute that spin component, that's given by the this is given by the Pauli matrix, which we'll call sigma y, and sigma y is 1/2 0 1 1 0 in the basis that we're using. So then, if you wanted to then say calculate, well, what is the expectation value of y? So what my formalism tells me to do is, if I want to compute this at the expectation value, what I have to take is the trace of the density operator times the operator that I'm interested in, which is sigma y. And so what that means is, let's do this now for the different pure states that we've considered. So case 1. So rho is equal to 1 0 0 0. So if we use this matrix, then sigma y is equal to the trace of this matrix 1 0 0 0 times the 0 1 1 0. And so now what I have to do is I multiply those matrices together, and you can quickly see that the diagonal element of this, adding them up, is equal to 0. Okay, so that again says that if the spin is pointing up, it's the expectation value in the y direction is equal to 0. Now let's take this case. So now we're going to say that rho is equal to 1/2 1 1 1 1. So that's the other case that we considered. So now what we have to do is compute sigma y to be the trace of 1/2 1 1 1 1 times 1/2 0 1 1 0. And so if I multiply those matrices together, what I have to do is to get the trace of 1/2 times 1/2 is 1/4, and then work out the matrix elements. So 1 times 0 is 0, plus 1 times 1 is 1. So I get 1, and then 1 times 1 plus 1 times 0 is 1. 1 times 0 plus 1 times 1 is 1. And 1 times 1 plus 1 times 0 is equal to 1. So now I have to work out the trace of this matrix. And now then the trace is just the sum of the diagonal elements. So I add up those two elements. So I have 1 plus 1 is equal to 2. That's divided by 4. And so I simply get plus 1/2. And so the expectation value is plus 1/2. So in this state, it's got an expectation value of pointing 1/2 in the y-axis. All right, now let's do the last case. So case 3, I'm going to take the density matrix to be 1/2 into 1 minus 1 minus 1, 1. So now all I've changed is the off-diagonal elements. And now if I compute the expectation value of sigma y, so this is going to be the trace. And I'm going to run out of space here, so let me do this down here. So I'm going to multiply again this density matrix times the spin matrix, and now again, when I work out what the matrix is, so I get 1/4. Now I have 1 and it plus minus 1, so now I get a minus 1 up here, a 1 here, a 1 here, and a minus 1 over here. So as a result of the change in the off-diagonal elements, so these are the off-diagonal elements. As a result of that change, what's happened is that's now made a change to the diagonal elements of the expectation value. And so what I end up with here is minus 1/2 for this case. And so again, what we've seen then is that this formalism is giving you exactly the same results that you would get from quantum mechanics. Okay, so now that we've done that, let's go on to a more interesting example. So the next example I want to talk about is the density matrix for a single spin, but in a mixed state. So what I'm going to do is I'm going to write down what the density matrix is. So in our general way of writing it down, it's some probabilities that I'm free to specify, and then the eigenstates n like this. And so this is the mixed state. And just to make sure that you fully remember this, if this was a pure state, so that's what we were dealing with before. So the pure state was like this, and then the pure state, if I wrote it down in terms of eigenstates, would be the sum over n. The sum over n, those expansion coefficients, an am star times n m like that. So this is pure state. So you can see very clearly the difference here in the pure states. We have off diagonal elements. Where n is not equal to m, and in this case here we only have diagonal elements. And so n is equal to m, so here there is a double sum. And here there is only a single sum. And so that's the difference between the pure states and the mixed states. Okay, so I'm repeating myself, but I want to make sure that everybody understands that. Now the other thing is, of course, that these p's have to be probabilities. So the Pn represent probabilities. And so that means that the Pn's must be non-negative. and their sum must be equal to unity. Okay, so let's now think of a mixed state that looks like this. So what we're going to consider is now some experimental situation, maybe made in some kind of Stern-Gerlach apparatus or something like this. Somehow you make it so that 50% of the ensemble is in this state, psi1, which is 1 over the square root of 2, 1, 0 plus 0, 1, and 50% in the state psi2, which is 1 over the square root of 2, 1, 0 minus 0, 1. So we're going to look at a system like that. So then what that says is that in this situation, the density matrix is 1/2 rho 1 plus 1/2 rho 2. And let's write down what those density matrices are. So rho 1 is the matrix 1/2 1 1 1 1 that we saw before, and rho 2 is equal to 1/2 1 minus 1 minus 1 1. Okay, so those are the states that we're adding incoherently here. And so now if we then go and work out what is the density matrix, so the density matrix is now then 1/2 times 1/2 1 1 1 1 plus 1/2 1/2 1 minus 1 minus 1 1. And if we add those up, what you get is just 1/2 1 0 0 1. You can see that the off diagonal elements have cancelled out. And in this mixed state, if I were to compute, say, the expectation value of sigma y, that would equal 0 in this particular state. So that's fine. So now the next example I want to look at is an example where we're actually doing statistical mechanics. So far, everything that we've talked about has just been some playing around with quantum mechanics. So now let's do an example where we're going to be doing statistical mechanics. So the only difference is that the PNs come from Boltzmann statistics. And the system that we're going to consider is a spin in an external magnetic field in thermal equilibrium. And so this is in other words, this is just the quantum paramagnet. So we already know the answer to this because we already worked it out. But let's go ahead and do it anyway. And I'm going to make it a spin 1/2. So we did it more generally. So what we're going to think of then is the way we're going to set up the problem is we're going to write down the Hamiltonian. So the Hamiltonian is minus G times the Bohr magneton times the spin operator dotted with the external magnetic field. And because the external magnetic field is going up the z-axis. This is just minus g times the paramagneton times sigma z times the magnitude of the external field. And this g, this is the Landé g factor, which is equal to 2 for spin a half. And I'm going to write down the Pauli matrices. So sigma z is equal to the matrix we saw before, 1, 0, 0, minus 1. Sigma x is equal to 1/2, 0, minus I, plus I, and 0. And sigma y is equal to 1/2, 0, 1, 1, 0. Okay, so those are just the usual Pauli spin operators for this quantity, for the Pauli operator. Okay, so now what we're supposed to do, now that we've set up the problem, what the next step is to write down the density matrix. So this is just e to the minus beta times the Hamiltonian over the partition function. And the partition function is just the trace of the matrix. And the way I'm going to write this operator is I'm going to write it in the basis of 0, 1, and 1, 0 that we've been using before. So just the basis pointing up and pointing down. So in this case, then, what is the matrix? So the matrix looks like this. So it's the state 1, 1 times the energy e to the minus beta E1 plus the operator 2, 2, that's the second one, times e to the minus beta E2, and then that's divided by the partition function, which is e to the minus beta E1 plus e to the minus beta E2. And in writing down this equation, what I've written down is that the eigenstate 1 is just the operator 1, 0. The operator 2 with that state is just 0, 1, like so. And then what are the energies in those states? Well, it's just reading off from the Hamiltonian over here. So I can then read off that the energies are minus mu b times b, and E2 is equal to plus mu b times b. So now I know the energies, so then I can write down what the density operator is, or the density matrix. So it looks something like this: e to the beta mu b times b, 0, 0, and e to the minus beta mu b times b. So that's my density matrix, but it needs to be normalized, and it needs to be normalized by the partition function, which is e to the beta mu b times b plus e to the minus beta mu b times b, like that. Okay, so now now that I know the density operator, I can then compute anything that I want. So let's suppose that I decide that I want to compute the magnetization in the z direction. So what that is, that's the expectation value of sigma z. So this is g times mu b times the trace of rho times sigma z. And then if I just now multiply this the matrix rho and sigma z out, what you will see is that this is equal to mu b times the hyperbolic tangent of mu b times b over bt. And this is something I want you to check for yourself. And this is, so we can compare with what we did before. So what we did before was we calculated this in terms of this non-Lagrange function, Brillouin function, Bj, compare with previous results using the formula Bj, and we simply set j is equal to 1/2, and you'll see that it completely agrees. So these examples then show you how one can use the density matrix in practice, and again, this is just showing you a very simple examples. If one is doing quantum many body theory, say for conventional physics, then this is the formalism that people often use. Okay, so I don't propose to do any more on that. What I want to do now is start the next chapter. So the next chapter in the course is interacting systems. So what is our goal here? Well, we know that real systems have interactions. So of course, what our goal is to try to understand what are the effects of these interactions. And we're going to see that there's basically two main effects. So the first thing is this. We're going to see that if we include interactions, we get quantitative corrections to the results of ideal theory. So as a concrete example for that, we might be thinking about the ideal gas formula. And what we might be asking is, well, if I include interactions, then we want to see how this changes. And we want to actually learn how to work that out in a systematic way. So this is a quantitative correction to what you get in the ideal case. The other goal that we're going to look at is that sometimes the effects of interactions are so severe that you get a change of state. So an example of that would be if I start off with a gas and I increase the density, then eventually it might become a liquid or even a solid. So those are states that are qualitatively different from a gas. And so the important word here is that there is a qualitative change to the system. I can't really think of a crystal as being anything like a gas. They're very different from it. A liquid, you might say, it is pretty much the same as a gas, except it's got a higher density, and that in fact is true. In fact, there is no real distinction between a gas or a liquid, and so we tend to use the word fluid to describe that. Now, these two differences turn out to be reflected in the mathematics of interacting systems. So what we have here is qualitative versus quantitative differences. Show up mathematically. So if we're talking about the case of a qualitative, well, let's just start off with this one, a quantitative difference. So how do we see a quantitative difference? Well, if it's quantitative, meaning maybe a small change, hopefully these corrections might be small, then what that means is that we can do perturbation theory. And we might hope that we can get some sort of finite radius of convergence for the perturbation theory, and so be able to make the specific corrections to the equation of state. So quantitative means perturbation theory is valid, and may even have a non-zero radius of convergence. In other words, what we're thinking of is that everything is analytic. And so that's going to be what we're going to be looking at. Now, when we turn to qualitative differences, then what's happening is that, e.g., say a solid is not directly related to a gas. And so because a solid is not really directly related to a gas, meaning you can't get there perturbatively, so my handwriting is pretty crappy there, let's try it again. So you cannot weakly perturb a gas and get a solid. And why can't you? Well, in a gas, I mean, roughly speaking, everything in a gas is sort of flying around in space, and everything inside a solid is basically stuck or localized. That's a very crude way of saying what is the difference between a solid and a gas. A better way is to say that actually what you have is you have a broken symmetry, and that reflects, or that's reflected in a non-zero shear modulus. So in other words, if I take a fluid or liquid or gas and I shear it and I wait forever, so that's what I mean by saying static, then it will eventually flow into whatever shape you turn it into. Whereas a solid, if you try to shear it or deform it, it will resist that deformation. and it will do so forever, and that's what we mean by saying it has a static shear modulus that is non-zero. So the connection between these statements is non-trivial. So how they're connected, that's something that we will to some extent talk about in this course, but is more something that we will talk about in the course emergent states of matter. Now, in terms of the mathematics, how is this reflected in the mathematics? So this is reflected in the fact that perturbation theory must fail, and the statistical mechanics and by which I mean the partition function is non-analytic as you go through a phase transition. So basically, what you've learned from this is that perturbation theory is most interesting when it breaks down. And why do I say it's most interesting? Well, that's just because finding some quantitative effect of an interaction, changing the equation of state, well, that's certainly interesting. I mean, you certainly could want to know that. You certainly might want to know, how is the band gap of silicon affected by, various effects. That's obviously technologically super important. So we certainly want to know how to answer those kinds of questions, but they're not terribly interesting from the theoretical point of view. On the other hand, when you have a total breakdown of perturbation theory, a qualitative change, a change of state, a phase transition, that's something that is much more interesting. Because one of the tasks of statistical mechanics is to try to work out what is the behavior of matter under different conditions, as you vary, the pressure and temperature and so on and so forth, external magnetic fields. And so those are the things that we are most interested in just knowing what the state of matter is. And so this whole breakdown then determines the phase diagram of systems. Okay, so let's very quickly remind ourselves what are the sort of interactions that we're typically going to be dealing with. So mostly what we're going to talk about are interactions which are between particles. And we're going to do in this chapter of the course two things. One, we're going to look at interacting particle systems, such as atoms or molecules. So we're going to do that using diagrammatic perturbation theory. So I'll show you how one does that. And then what we're going to be looking at for the qualitative differences, we're going to be looking at spin systems. So let me just write that down. So the quantitative effects of interactions. So the example that we will use is a non-ideal gas. And then for the qualitative effects, the example that we'll use is an interacting spin system, so we'll use the Ising model. And what we're going to do in terms of techniques, what we're going to learn here is we're going to use diagrammatic perturbation theory. And then here, what I'm going to be teaching you is mean field theory. And also we'll look at the Yang-Lee theory of phase transitions. Actually, the Yang-Lee theory, for that we will look at gas systems as well. So this will be different from what I cover in the renormalization group course, and we'll see that the mean field theory, though, actually is very powerful. We can see scaling laws and universality. We'll see all of these things that come out in mean field theory, and we'll talk very briefly about how these results get corrected by a renormalization group. Okay, so now let's talk about the nature of interactions. So, so what I'm basically going to be thinking about is, so let's suppose I've got two atoms at some point R1 and R2 like that, and what we're going to ask is, well, what happens as we what happens as a function of separation on. So at short distances, at short separations, we know what's going to happen is there's going to be a hardcore repulsion. And that hardcore repulsion is going to arise through the overlap of electrons. Fundamentally speaking, so that's what happens at short distances. At long distances, what you have is you have van der Waals interactions. And what these are dipole interactions. So let's sort of see how they come about in some very simple cartoon way. So here I want to think about my two atoms, and what I'm going to sketch now is the a snapshot of the system. So let's suppose, for example, I take a snapshot of this system here. So let's suppose that the electron cloud looks something like this. So this is going to have a dipole moment. So it's going to be plus in this direction, minus in this direction, and there's going to be a dipole going like so. Now let's suppose that this is a snapshot. So what is that going to do? Well, what's going to happen is the electron cloud around this atom is now also going to adopt a shape like this. But what's going to happen is that you're going to have the electrons here. This is going to be minus, and this is going to be plus, because the minus sign here is going to pull a net positive charge over to this side. And so what's going to happen is I'm going to get a dipole now, which is pointing down in this particular case. So let's estimate. So this is kind of like a snapshot followed by a small time interval. And there's a small time delay because what's going to happen is once the electrons here have formed some conformation, well, this charge has to this picture has to then be transmitted over here, and the electrons then have to relax to form this configuration. So let's work out then what the energy of the system is going to be in this particular case. So what we're now looking at is that the energetics is that of a dipole in an external electric field. Why? Because I've got this dipole over here, let's call it P1, and that then is going to create an electric field, which I'll call E1, and then this dipole here, P2, then feels the effect of the electric field, E1. So let's see how that works out. So the energetics is just given by the energy of a dipole in an external field E is given by P dot E. So that's just from basic electricity and magnetism, and the induced dipole moment P2 is going to be proportional to the field that is experiencing E1. And so what that means is that if I want to work out what the interaction energy is, how is that going to scale? So that interaction energy is basically going to go like alpha times E squared, where this alpha, I didn't say what it was, but I should have done. So this alpha is the polarizability. So what is well, how does E scale? So to answer that, we can just remind ourselves that if I have the scalar potential from a single charge, so that goes like this is a sort of coffee shop derivation. So this goes like 1 over r for a single charge, and for dipole it goes like 1 over r squared. So therefore, the electric field, which goes like minus grad of the scalar potential, is going to go like 1 over r cubed, and so therefore, since E goes as 1 over r cubed, what we've learned is that U is going to go like 1 minus 1 over r to the 6. So now what we can do is we can build a model of the potential. So it's hardcore at small distances, and it goes like 1 over r to the 6 for large distances. So there's a nice parameterization of that. And so the parameterization that everybody likes to use is a parameterization due to Lennard-Jones parameterization. So this Lennard-Jones potential just says, well, let's write the interaction potential as a function of separation. That's going to go like minus some coefficient over r to the 6. And at short distances, it should be a very large and positive. So we'll write that down as some a over r to the 12. And there's no special reason for this r to the 12. It's just a functional form that rises steeply. And then the last term is just the long range attraction. So the usual way that we rewrite that, it has two parameters a and b. So the usual way that we rewrite it is like this. And what this means in terms of the actual potential, we can sketch it like so. So it looks something like this. So what we're plotting here is u of r, and comes down like this and goes like so. This point where it crosses is r naught. This depth here, this binding energy, is epsilon, and this distance here, where you have the minimum, that occurs at a distance which we'll call r star. So this r0 over here, this is just the hardcore radius. And this is the binding. Okay, so let's make a couple of comments. So the first thing is that this is isotropic, and because u, which could in principle depend on the vector r, is actually just a function of the scalar r, the magnitude of this vector. So this is isotropic. Now this isn't necessarily true for all systems. It's easy to think of many systems that don't have, they're not isotropic, but have direction-dependent forces. So they do exist. Such as covalent bonds, hydrogen bonds, ionic bonds, and so on and so forth. So that's true. There's also you can also have long range forces. And what we're going to see is that they actually need to be treated specially. So special treatment of electrolytes. And we'll see that these long range forces cause a particular problem in the diagrammatic perturbation theory that we're going to be using. You know, the other comment that I want to make is that this is comment number 1, comment number 2, comment number 3. So comment number 4 is that we have assumed pairwise additivity. So what we mean by that is that we can write the total potential, say, for a bunch of particles with positions Ri, and we can write them as the sum over I and J of some pair potential Ri minus Rj, something like that. So this is in fact what we will typically do, but it's not always correct. And in principle, you can have terms that are not reducible into pairwise terms. And why would that happen? Well, you can think of it in the following way. Let's suppose that I have two particles. So here, particle number 1 and particle number 2. So they're just sitting there and they're interacting. And I take these two particles 1 and 2, keep everything the same. But now what I do is I bring up a third particle number 3 from infinity. And now what's going to happen is this particle over here is going to, as it were, distort the electron clouds around this one. It's going to distort the electron clouds around this one, and this amount of distortion will depend on R1 minus R3 and R2 minus R3. And so what that means is that you can see from this that it implies that there must be a term that depends on R1, R2, and R3. And that's this term that I'm drawing over here. So these are three-body interactions can make a big difference. So, for example, if I'm looking at, say, argon liquid, and I think I spelled it wrong, didn't I? So argon in liquid, its energy is about 10% free body terms at room temperature. And some high pressure. So this pairwise additivity assumption here is it does need to be thought about. It's non-trivial, and you might wonder, well, why is it that we work so hard to compute accurately an answer that we know must inevitably be wrong, because we're going to be leaving out terms that are more that make a bigger contribution to the energy than the ones that we're computing, and that's a perfectly sensible question. Okay, so now what our goal is, let's see how we're doing for time. We've still got time. So the next thing that we want to work out then is how to compute the effects of pairwise interactions on the ideal behavior. And so the way I'm going to approach this is we're going to use the Virial theorem that I proved for you before. And so the way I want to set this up is using the Virial equation of state. So There's a couple of derivations in this class that are quite complicated. So I've derived for you the ideal gas equation of state in a fairly complicated way in the course using delta functions and things like that. What I'm going to do now in the next couple of minutes is I'm going to derive the ideal gas equation of state in the most elegant and simple way that I know, a beautiful way, and so we'll see that. The other thing is I want to point out is that we're coming up to a lecture which I like to call the lecture from hell, because it's a lecture which is purely on graph theory to try to explain how one does these diagrammatic perturbation theory things. And in that lecture, even though it's quite complicated technically, what I'm going to ask you to do is focus not on the algebraic details, but just the general picture, and then to follow the details of yourself if you want. Okay, so let me say what my goal is now. So the goal in this section is, first of all, I want to show you how one can use the Virial theorem to compute the equation of state. What we're going to do is do this for the ideal case, ideal gas, and then what we're going to start is the corrections to it using perturbation theory. Okay, so let's just remind ourselves what the Virial theorem says. So what we proved was the Virial theorem that if I took the expectation value of the sum from I equals 1 to 3n of the coordinates times the time derivative of the generalized momenta, then this was equal to minus 3 n kbt. So that was an exact theorem. So what we're going to see is that when we compute using diagrammatic perturbation theory, and I think I'll add this right up here, what we're going to see is that there's a connection between the equation of state and the 2-point correlation function. So one of the things that we're going to be doing in this part of the course is we're going to be introducing the idea of correlation functions and showing how they're defined and how we compute them. So let me explain why correlation functions come into this. So if you ever go and visit ICMT, you'll see people always writing on blackboards. They'll be writing Feynman diagrams or other kinds of diagrams, and they'll be computing correlation functions. Why do we care about this? So roughly speaking, we're going to get into this in more technical detail later. What the 2-point correlation function measures is it measures the probability of finding a gas particle distance r away, or even a vector r away from a test particle. in thermal equilibrium. So that's roughly speaking what it is. So So let's just take that as given. So why is it going to come into our considerations? Well, let's think about a case with no interactions. So if there's no interactions, then the probability of finding another particle a distance r from a given particle is it going to be independent of r. And it will just depend on the density. Which is just the number of particles per unit volume. And so this probability, so there's this second particle is not affected by the test particle. So that's the case when there's no interactions. Now switch on interactions. So now what's going to happen? So when you switch on the interaction, so now what's going to happen is that the probability is that the test particle will influence the probability that we're looking for, and it will depend on the distance between the particles. So it will have to depend on r. The other thing is the long-range attractions between the particles are going to cause the particles will cause them to collide with the walls of their box less. And why is that? Well, we can just draw a very simple cartoon. So here is a box, particles, and I'm going to draw two cases, one which is with no interactions and one with interactions switched on. So in this case, what's going to happen is the particles are just bouncing around and they're crashing into the walls, and so the collisions with the walls give you the pressure. Now in this particular case, when the interactions are switched on, the particles have some long-range attraction, and so you can think of it in sort of cartoon language, is that therefore because they self-attract, they hit the wall less. And if they hit the wall less, then that's going to mean that the pressure is going to go down. And so what this simple argument then shows you is that the interactions do two things. They cause the particles to become correlated, meaning that their probability of finding a particle over here and a particle over here, those positions now depend on the distance. So that's an obvious effect of the interactions. And then the second thing that they do is that they reduce or change the number of collisions with the walls i.e. the pressure. And so what that therefore must mean is that the pressure of the system must then depend on the correlations between them. So in other words, we expect that the pressure is going to be some function of the correlations. And indeed, that's what we're going to see. So what we're going to see next time is that how to write down the equation of state in terms of the correlations between the particles. Okay, so I'm going to just go on for just a couple more minutes. So let me now just finish this off by showing you the quickest and most succinct derivation of the ideal gas. Okay, so here's the basic the picture. So in the ideal gas, the only forces are due to particles interacting with the container walls. So let's work out what the virial is. I'll write it down as a capital V. So I'm going to write it down as the expectation value of this, and the rate of change of momentum. This is just given by Newton's equations. That's equal to the forces. The forces exerted on particle I. So what I've written down here is Newton's equation is Pi is Fi dot. So what actually are those forces? Well, they're only with the walls of the system. So here is the system. Here is the wall, and now what's happening is a atom is coming in like this, bouncing off the wall, like so, and it's going to exert a force. So we'll write the force down like this. This is the force that it exerts, and what we're going to write down is we'll write a little element of surface area, ds, which looks like this, pointing out like that. So this is an element of surface area. Okay, so now what is going to be the rate of change of momentum? So what's happening is that we define the force in terms of the pressure, and that's defined in the following way: the force exerted by particle I in making this collision is equal to minus the pressure times the element of surface area ds. And it is a convention that that we have this minus sign here. So the pressure is exerted this way, and ds is pointing outwards. Okay, so that's the picture. So now what we're going to say is this: we're now going to cause graininess. So this is just one collision that I've shown you over here. We're going to cause grain this type of collision over the surface of the container. So what that means is that when we average over a region of the surface, the qi turns into the vector r. That's just the component, and so I can write this quantity, the virial, as the following: I'm summing from I equals 1 to 3n qi times the force, and so this is going to be now an integral over the surface. So this is going to be minus the integral over the surface, and it's going to be the force, which is P times ds. So P is the direction, the pressure is force per unit area, so it's P ds, and then Q times the force is R dotted with the P dot ds. So that is going from here to here. This is a coarse grain. All right, so now let's evaluate this thing. So this integral here, the pressure just comes out, and then this is the integral of R over the surface of the container, R dot ds, and we can, for this integral here, we can use the divergence theorem. So the divergence theorem says that if I have an integral over a surface, then that is equal to an integral over volume. So this thing is equal to the integral of the divergence of whatever vector this is, in this case it's r, integrated over the volume of the container. So that's what the divergence theorem tells us. This quantity over here, this is the virial. So what I've just calculated then is that the virial, written down with this sort of fancy v, is equal to minus p, that's this minus p over here, times the integral of div r dv, and that is equal to minus p times the volume, which is v, and then div r is just 3. So what I've shown you is that the virial is equal to minus 3 PV. So now, excuse me, I'm in class. So that means then, we're using the virial theorem, that 3 times PV is equal to 3 NKBT, and that 3 is the same 3 that is in the virial theorem over here. So then just dividing through by the 3's, what I've then derived for you is that PV is equal to NKBT for an ideal gas. Now I went and explained it in great length, but I think you can see that this derivation is very succinct and really quite beautiful. Okay, so that's where I'm going to end today's lecture. So next lecture, we will start by asking what happens to the virial when we start putting in interparticle interactions. And so that's where I'll end today's lecture. Any quick questions about today's lecture before we turn off the recording? Ching Hao.
How we find out the contribution for the three-body interactions is 10 percentage for the algorithms.
How do we know that? We only know that by doing detailed molecular dynamics calculations that sort of take into account the quantum mechanics and the orbitals and so on and so forth. So there's no way you could know that just from just the sort of things that we've been doing here. It's an empirical fact.
Okay.
And you can calculate it, and I think you can measure it as well. So I'm mentioning it just to warn you that one shouldn't always when one assumes pairwise additivity, we always start off in statistical mechanics like that, but it's not always the correct thing to do. Okay, well, if there's no other questions, I will have an office hour at 4 o'clock, and I'll try to be there for all of that. It's possible that I won't be able to make it. I have a number of other meetings that will clash with it today, but I'll do my best. Okay, so at that point we will end the lecture. So goodbye, and see you next time.